A morning on what will one day be called Antarctica. The sun is up, but only barely. The light is thin and silver, the kind of light that comes through high cloud at a high latitude. A single set of footprints is pressed into frost-glazed mud beside a slow-running creek. The animal that made them is standing at the edge of the water now, head lowered, drinking. It is 2 meters tall at the hip. It walks on 2 legs. There is a thin, bony crest running across the top of its skull, a curve of bone that catches the cold light like a coronet. From its nostrils, 2 pale plumes of breath rise into the morning air. The breath is visible, which is to say, the breath is warm. This is not supposed to happen. For most of the previous 200 million years, an animal this size, in a place this cold, would have been a problem in physics. Reptiles take their temperature from the world around them. In cold, they slow. In deeper cold, they stop. They are governed by the sun, and yet here, in a frosted Antarctic valley 190 million years ago, an animal that looks unmistakably like a reptile is standing in the cold, breathing visibly, very much not slowed. Somewhere in the last 20 million years, something extraordinary has happened to this lineage. The animal lifts its head. Frost falls from its jaw in a small, bright shower. It turns, unhurried, and walks away from the creek. In its body, something is burning that was not burning before. How did warm-bloodedness begin? And what was the world doing to its inhabitants the day that one lineage of dinosaur decided it would never again wait for the sun to rise, to be itself?
This is Cosmic Canvas.
This is the Mesozoic. This is Episode 2, The Hot Inheritance. To begin, we have to return to a morning the planet was still recovering from. When we left the world, it had just ended. The Central Atlantic Magmatic Province had torn Pangaea along the line that would one day become the Atlantic Ocean, pumping carbon and sulfur into the air in pulses that may have frozen the planet over and over for tens of thousands of years. 201 million years ago, 3 out of every 4 species on Earth were gone. And then the eruptions stopped, and the sky cleared, and the sun came back. And on the morning after, which is to say, in the geological dawn of the Jurassic, the survivors began to look around. There were not many of them. What was left was small. Almost everything large had died. The phytosaurs and the Rawasuchians and the great Triassic dicynodonts that we met in the last episode, all of them gone. The crocodile cousins had been reduced to a handful of small, fast, mostly aquatic survivors. The synapsid line, our line, the line that would one day produce mammals, had been reduced to small furred animals barely the size of a shrew, hiding in the dark hours. And there were the dinosaurs. They had walked through. We do not know exactly how. We have guesses: efficient bird-like lungs, faster growth rates, perhaps a slightly elevated baseline metabolism. But whatever the combination, more dinosaur lineages had survived the cold than not. And now, in a planet that had been emptied of competition, they began to grow. The early Jurassic is the moment when dinosaurs stop being supporting cast. It lasts about 27 million years, from the dawn of the Jurassic at roughly 201 million years ago, to a moment we will return to near the end of this episode at 174 million. In that window, on every continent that still bore witness, the survivors began to test what they had inherited. We can follow them. In southern Africa, in what is now the Karoo Basin of South Africa and Lesotho, the rocks of the Upper Elliott Formation begin to fill with the bones of a single species, a slender, long-necked, two-legged plant eater, roughly 4 to 6 meters long, with a small head and a heavy tail. Its name is Massospondylus carinatus. It is one of the most abundant early Jurassic dinosaurs anywhere on Earth. More than 200 specimens have been recovered. Hatchlings, juveniles, adults. A complete arc of a single species growing up. Massospondylus is small by the standards of what its descendants will become. 500 kilograms is roughly the maximum. But on the same floodplains alongside it, you would find other shapes already starting to grow. Some, like the rare giant Ledumahadi, an early Jurassic sauropodomorph from Lesotho with the bulk of a small elephant, were already pushing past 4 tons. The lineage is finding its scale. And it is finding something else, too. Something that does not show up in bones, that has to be argued from softer evidence. In 2024, a team led by Robert Rice at the University of Toronto published a paper in Scientific Reports in which they did something quietly extraordinary. They took the embryonic and hatchling bones of Lufengosaurus, a close cousin of Massospondylus, found in southern China, and they compared the rate at which those bones developed against modern bird embryos, specifically against 2 birds with very different baby strategies. Chickens, whose hatchlings come out of the egg ready to walk, feed themselves, and survive on their own, and pigeons, whose hatchlings come out blind, naked, helpless, and entirely dependent on parental feeding. The Lufengosaurus hatchlings, they found, looked like pigeons, helpless, underdeveloped, unable to forage, almost certainly fed by a parent for some critical window after hatching. Which means, if the result holds, that in the early Jurassic of southern China, 200 million years ago, a parent dinosaur was carrying food back to a nest of crying juveniles. Not in the late Cretaceous, not in the famous duck-billed nesting colonies that paleontologists have known about for half a century. Here, in the lineage that would one day become every sauropod that ever walked. The dinosaurs of the early Jurassic were not just inheriting an empty world, they were finding out that they could take care of each other in it. This is the second thing we have to unlearn. For most of the 20th century, dinosaur parental care was understood to be a late Cretaceous innovation. A clever trick that the most advanced groups picked up near the end. The new picture pushes that trick back by 130 million years, into the earliest fully developed sauropodomorphs, into the morning of the Jurassic itself. The lineage that would one day include the largest land animals that ever existed began as a clutch of helpless babies whose mother brought them food. This is what we mean when we say that the dinosaurs of the early Jurassic were not the dinosaurs of the Triassic anymore. Walk 3,000 miles north of the Karoo, across what is now becoming the North Atlantic, and you find yourself in another early Jurassic floodplain. The rocks here will one day be called the Kayenta Formation. They sit in northern Arizona, in the high red country of the Colorado Plateau. The Kayenta is hot, not desert hot. There are streams and ferns and stands of conifers along the water, but warm, dry, and seasonal, the climate of a place that is slowly drying out year over year. And walking through it is a 6-meter theropod with a strange double crest running along the top of its skull. Dilophosaurus weatherilli. You have probably seen this animal before, or you think you have. In 1993, a film made Dilophosaurus famous in a particular form, a small, frilled creature with a venom-spitting hood. That animal is not real. The real Dilophosaurus was twice as long as the film version, 6 to 7 meters, perhaps 400 kilograms, a serious apex predator, the largest carnivorous animal in early Jurassic North America. It had no neck frill. It did not spit venom. What it did have were the two thin, bony crests on its skull that gave it its name, Dilophosaurus, the two-crested lizard. The crests were not weapons. They were ornaments, display structures, almost certainly used in the same way a peacock uses a tail, to be seen by other Dilophosaurus in the brief seasonal windows when seeing each other mattered. This is itself a kind of revelation. The dinosaurs of the Kayenta are not just predators and prey anymore. They are animals that have started to decorate themselves for each other. Now walk further, east across what will become the Atlantic, then south down the spine of Gondwana, until you reach the southern tip of what will one day be Antarctica. In the Transantarctic Mountains, 4,000 meters above sea level, there is a rock formation called the Hansen. It was laid down between about 194 and 188 million years ago, in the Sinemurian and Pliensbachian stages of the early Jurassic. The continent was not yet polar. It sat at a high latitude, but the climate was cool temperate. Forests of conifers and ginkgos, streams, lakes, an active volcanic rift system splitting Gondwana apart underneath. And in those forests lived an animal with a name that almost feels like a joke. Cryolophosaurus ellioti, the crested cold lizard. A 6.5-meter theropod with a transverse bony crest running across the top of its skull like a fan. A single, dramatic, swept-back ridge that has earned it a nickname in the paleontology community, Elvisaurus. Cryolophosaurus is the largest theropod known from early Jurassic Antarctica. The animal we met at the beginning of this episode, standing at the frosted creek with visible breath, that was a Cryolophosaurus. It hunted in a cool, temperate forest at high southern latitude, alongside a basal sauropodomorph called Glacialosaurus, alongside small synapsids the size of rats, alongside fossil tree trunks 2 meters across, and alongside one other thing, which is the reason the whole episode pivots on it. The plumes of breath. You can only see your breath when the air is cold and the body is warm. In a reptile that takes its temperature from the world around it, the breath leaving the nostrils is the same temperature as the air entering them. Nothing fogs, nothing visible escapes. A modern crocodile in winter does not steam. If the air outside is cold, and the breath coming out is fogging, the inside of the animal is warm, hotter than the world, burning fuel to make that heat. Self-heated. Endothermic. We could not, of course, see the breath of a Cryolophosaurus directly. Soft tissue does not fossilize. But the fact of where Cryolophosaurus lived, at a high-latitude site, in a cool, temperate Jurassic climate, in numbers, is by itself a strong hint. Cold-blooded reptiles do not flourish in cool, temperate forests. Warm-blooded ones do. Something in the lineage that produced Dilophosaurus and Cryolophosaurus had changed. For most of the 20th century, paleontologists argued about whether dinosaurs were warm-blooded or cold-blooded, as if the answer had to be one or the other, as if all of them, all the time, had run on the same engine. They did not. The question that took 100 years to ask correctly was not whether, it was which ones, and when. In May of 2024, A team led by Alfio Alessandro Chiarenza at University College London published a paper in the journal Current Biology that proposed an answer. They did not look at bones. They looked at maps. More precisely, they looked at where every well-dated dinosaur fossil had been found across roughly 200 million years of dinosaur history, and they reconstructed the climates those places had at the time of fossilization. Temperature, rainfall, seasonality, the whole envelope of conditions that an animal living there would have had to tolerate. And then they tracked how those climate envelopes shifted across the dinosaur family tree, which lineages moved into colder climates, which stayed in the heat, and when. What they found was a hinge. Around 183 million years ago, two of the three main groups of dinosaurs broke their old climate ceilings and began to expand into colder, higher latitude environments. The theropods, the lineage of Dilophosaurus and Cryolophosaurus, and eventually every meat-eating dinosaur and every bird that has ever flown. And the ornithischians, the lineage that would, in time, produce Stegosaurus, Triceratops, Iguanodon, the duckbills. Both lineages, at roughly the same moment, began doing something no large reptile had ever done. They walked into the cold, and they stayed. The simplest explanation, the one Chiarenza's team proposed, is that they had become warm-blooded. The third group, the sauropodomorphs, did not. Massospondylus and Lufengosaurus and their descendants, the long-necked giants of the Jurassic, stayed where it was warm. Their family tree across the next 120 million years tracks the equator. When the climate cooled, they moved with it. When it warmed, they followed. They had chosen a different solution. They had grown enormous. A large enough body holds its heat the way a stone wall does. The inside takes a long time to cool, even if the outside is dropping. We have a name for this: gigantothermy. It is the strategy of a creature so large that it makes its own weather. The sauropods, in time, would become the largest land animals that have ever lived. Tens of meters long, tens of tons. Walking furnaces of inertia. They did not need to burn fuel to stay warm. They were warm because they were enormous. Two strategies, the same kingdom, diverging from the same ancestor in the same epoch in response to the same trigger.
And the trigger was a crisis.
Around 183 million years ago, the lithosphere underneath what is now southern Africa and Antarctica began to open. Lava welled up, a great deal of it. We call the resulting volcanic province the Karoo Large Igneous Province. Karoo for the South African basin where its lava flows are most visible today, Forage for the volcanic intrusions in Antarctica. Between them, the eruptions released vast quantities of carbon dioxide into the atmosphere, both directly from the lava and indirectly by baking ancient organic-rich sediments and venting thermogenic methane. The result, on land and in the ocean, was a hyperthermal event, a brief, intense pulse of global warming. The geological name for it is the Toarcian Oceanic Anoxic Event, after the period of the Jurassic in which it occurred. The geochemist who first described its signature was named Hugh Jenkyns, and so today the event is more often called by his name, the Jenkyns Event. Sea surface temperatures rose by 4 to 7 degrees Celsius. The oceans, in places, lost their oxygen. Forest fires spread across continents. Acid rain weathered the land. Some of the plant communities that had defined the early Jurassic disappeared. It was, as these things go, a minor mass extinction. but a real one. And it is in the millions of years following the Jenkyns Event that the climate envelopes of theropods and ornithischians begin to cool. The picture that Chiarenza's team draws is this. The world warmed. The forests that the early dinosaurs had been comfortable in burned and shifted. The lineages that could not handle the change either died or moved. And the two lineages that moved, the theropods and the ornithischians, moved into colder country than any large reptile had ever inhabited, which they could only do if, somewhere inside their bodies, they had begun to generate their own heat. The Jenkyns Event may have been the environmental crisis that selected for warm blood. We are still piecing it together. The exact mechanism, what genes shifted, what tissues changed, what the first warm-running theropod actually felt like in its own ribcage, is something we may never directly recover. We are reading the answer from where the bodies ended up buried, rather than from the bodies themselves. The argument will continue. But here is what is no longer in doubt. By the end of the early Jurassic, in the high latitudes of an Earth that had been a hothouse for 200 million years, two of the three main dinosaur lineages had stopped depending on the sun to make them work. They were carrying summer with them. There is no free lunch in physiology. Warm blood is expensive. A modern endotherm, a mammal, a bird, burns roughly 10 times the energy of an equivalent cold-blooded animal of the same size, which means it has to eat 10 times as much, which means it has to spend 10 times as long foraging, and risk 10 times as much exposure, and process 10 times the food through its gut, which means it has to be 10 times as good at finding food, or it dies. The first theropods and ornithischians that flipped the metabolic switch did not get a gift. They got a bill. You can see the bill in how their bodies changed. Their bones grew faster. Modern endotherms grow faster than ectotherms because their high metabolisms drive cell division. In the theropods, respiratory systems leaped forward. By the late early Jurassic, the avian-style flow-through lung, with its complex system of air sacs, was already in place. Their guts, almost certainly, processed food faster, though gut tissue does not fossilize, and we have to read this from the skeletons that supported them. And their lives got shorter. A theropod that burned this much fuel could not live 100 years. It probably did not live 30. The cost of being warm is being hungry, and the cost of being hungry is being mortal in a way a cold-blooded animal of equivalent size is not. But against this cost, look at what they got. They got the night. A cold-blooded predator at night in the Jurassic is a sluggish predator. A warm-blooded predator is not. Cryolophosaurus could hunt at dusk in an Antarctic forest. Dilophosaurus could be active at dawn before the desert heated up. And not just at the edges of the day. They got sustained speed, the kind that lets an animal run down its prey across long distances. Cold-blooded predators can sprint. Warm-blooded predators can chase. They got the poles. The high latitudes had been off-limits to large reptiles for the entire Triassic. By the late Jurassic, theropod and ornithischian dinosaurs would be found from the Arctic to within walking distance of the South Pole. They had inherited a whole hemisphere their relatives could not reach. And, though this would not pay off for another 60 million years, they got the architecture of flight. Birds are the most extreme endotherms on Earth. They have to be, because flight is the most energetically expensive thing any vertebrate has ever done. The lung, the bone structure, the hot blood itself. All of it is being quietly assembled, piece by piece, in the small, fast theropods of the early Jurassic, long before any of them will fly. But before we leave this world, there is one more thing worth looking at. It is 174 million years ago. The Jenkyns Event is finished. The world is cooling, gently, back toward its long-term average, and on a single floodplain, two animals stand within sight of each other, eating different things, governed by different engines. The first is a long-necked sauropodomorph the size of a small barn. It is browsing on the high fronds of a conifer, slowly, methodically, using the inertia of its enormous body as a thermostat. The sun warms it during the day. The mass of its body holds the warmth through the cold night. It does not need to do much else. The second is a 4-meter theropod, lightly built, walking around the edge of the same clearing. Its body is small enough that, in the Triassic, it would have had to wait for the sun to be active. But it is not waiting. It is hunting in the cool of the morning, ribs visible, breath fogging. It will need to eat several times today to keep this engine running. It will probably not live as long as the sauropodomorph, but it can do things the sauropodomorph cannot. It can hunt at night. It can climb. It can chase. Two strategies in the same clearing. For the next 110 million years, these two strategies will compete and coexist and elaborate and refine. The sauropods will become the largest land animals in the history of the planet. The theropods will become the fastest, the smartest, and, in their smaller descendants, the only ones who will leave the Mesozoic behind. Because the thing about endothermy is that, once you have it, you can shrink. A warm-blooded animal can be the size of a sparrow and still function. It makes its own heat from inside. A cold-blooded animal cannot be that small and still be active in a cold morning. Endothermy is not just the strategy that lets you climb into the cold. It is the strategy that lets you become tiny. And one day, 66 million years ago, when the next great extinction comes, the ability to be small and warm and inside a burrow is going to be the difference between extinction and a future. But that is a long way ahead. In the last episode, at the end of the Triassic, we said that the dinosaurs walked out of the extinction carrying a flicker of inner warmth. That small advantage in metabolism that helped them through the volcanic winters where larger and slower animals could not follow. This is what happened to that flicker. It split. One branch banked it. The sauropodomorphs took the warmth they had and used it as a starting kit. They grew large, then larger, then enormous. They used their size to hold heat against the night, against the seasons, against the climate. They became the great, gentle, warm-from-mass giants of the Mesozoic. And they did not need an inner furnace, because they had become a furnace themselves. The other branch fanned it. The theropods and the ornithischians took the small advantage they had and pressed it into something stranger and more demanding. They built avian lungs. They sped up their growth. They learned to eat several times a day. And 183 million years ago, when the world warmed and the forests shifted and the climate windows changed, they walked through the door no large reptile had ever walked through. They walked into the cold. This was the hot inheritance, not the world they were given by the survivors of the Triassic, the world they made warmer inside themselves than the world outside. We are still looking, of course. The exact moment when the first theropod ribcage held a true endothermic core is something we may never directly date. The Jenkyns Event is the strongest signal we currently have, but it is a signal read from where the bodies were buried, not from the bodies themselves. New work will refine it, new papers will argue with it. But what is not in doubt is the shape of the answer. By the middle of the Jurassic, 2 of the 3 great dinosaur lineages were burning their own fuel. And the descendants of those 2 lineages have not stopped burning it since. The robin in your garden has a core body temperature of about 41 degrees Celsius. Hotter than yours, hotter than any mammal, hotter than was strictly necessary for survival, but kept that way generation after generation for the last 183 million years. That is the signal. That is the inheritance. That is what the small, 2-legged hunter at the Antarctic creek, with breath fogging in the morning air, was already carrying, though it could not have known. In the next episode of this series, we will follow what happens to that fire as it spreads. We will meet sauropods so large they had to be 60 years old to reach their full size, and we will meet theropods so small that the line between dinosaur and bird stops being a line at all. We will meet the first true feathers. We will meet the first wings. We will meet the moment when the inheritance becomes a song. The flame is split. It is also still burning. This is Cosmic Canvas. Until next time.